Right. First of all, can you guys hear me? Okay, cool. Now today we have a very small attendance. I think that is because it's just after the exam. Now, do you guys have any questions from the exam or from your chapters 6 and 7, which are the chapters that we are going to cover today? Questions from previous chapters or questions from chapter 6 and 7? Questions? In that case, I selected 2 questions to work on. I didn't select a question from chapter 7, because chapter 7 questions are a bit more complicated. I don't think it will be effective to discuss them in the recitation class. They are much more suitable in the video format because those questions are longer and takes a lot of time, a lot of techniques. If you are intimidated by chapter 7, chapter 7 is entropy, which is a difficult subject to understand, and it is very difficult to explain, right? Because entropy doesn't have a physical feel for it. You cannot explain entropy in a physical manner. It's a very theoretical subject, so it's kind of difficult to understand. So don't get scared if you cannot understand what is entropy. Okay? My advice is don't try to understand entropy while you will go into later chapters. Okay? While you are covering chapter 7, your focus should be to understand the equations. So understand how to use those equations that is given in the equation sheet. Okay? Understanding why it happens can come later when we are applying entropy related theories. Okay. So let's go into chapter 6. In chapter 6, we talked about various thermodynamic devices, right? Heat engines, refrigerators, and heat pumps. Now, let me bring up this shell. Let's try to solve this problem. Okay. For the exam, I think solutions are available. Let me check. So how many of you can see the solutions for the exams? So if you can see the solutions for the exam, please say yes. If you cannot, please say no. I think the solutions for the exam should be available now. So at least one person says that he can see the solution. How about others? There should be at least 10 people in the class.
Where is it posted?
It should be in the eCampus. Sorry, Connect. Yeah, when you go to the Connect system, you should be able to see the solutions. Just like how you see the answers for the your homeworks.
I found it.
You found it? Okay, awesome. So solutions are posted. All right, thank you very much for participating in that poll. If you have any issues with the solutions, please let me know. Now give it a try to solve this problem. At least start solving the problem. Right? And let me know when you had enough time. Now, whenever you are dealing with one of these problems with a heat pump or a heat engine, refrigerator, any chapter 6 problem, you should start that with this diagram. Okay, you have your heat engine device in the middle, two reservoirs, low temperature reservoir, high temperature reservoir, and you have heat flows, two heat flows. These are your heat flows, and this is going to be your workflow, right? So this is your starting diagram. Now in this case, we are talking about a heat pump. Okay. Now in a heat pump, we are pumping the heat in the opposite direction to the spontaneous direction. Now for a heat engine, I'm not going to draw it here, but when you have a heat engine, what we do is we use the spontaneous flow of the heat to get some work out of it. Heat pump is the reverse of it, right? So we are pumping heat from low temperature reservoir to the high temperature reservoir. And to do that, we need some work input. So W dot is work input, QH dot is the heat output, heat input is going to be QL dot. Okay, L stands for low, H stands for high. Now in this case, we have a heat pump. We are given the temperatures of the reservoirs, 535 Kelvin and 460 Kelvin. So even though your questions are going to be MCQ questions, just write these things down so you don't have to go and hunt them later. Now we are asked to calculate the minimum work. Minimum work per unit of heat transfer from the source reservoir. Okay. Now, which one is the source reservoir? Source reservoir means that is where we get the heat from. So this is our source reservoir in this case. And this is going to be our sink, right? So this is going to be our heat transfer from the source reservoir. So we are asked to calculate the minimum work per unit of QL. So what we are actually asked to calculate is W dot in this case it's an input, divided by QL. And we are asked to calculate the minimum of that. Okay. Now you should be able to calculate this. Now when it comes to minimum, okay, minimum work input for a refrigerator or for a heat pump, like in this case, happens when we have reversible conditions, right? So let me write it here. For a refrigerator or for a heat pump, when we have Carnot, reversible conditions, that will give you W minimum. Okay? If you have a heat engine, when you have reversible condition, okay, you are going to get W maximum. So in this case, to get the minimum work, we are assuming that it is Carnot, reversible conditions. Okay. Now let's try to simplify this equation. Okay. Because we know in reversible conditions, when you have reversible conditions, QL over QH is going to be equal to TL over TH, right? So we want to get rid of this W to get an actual value for that. Okay, if we can write this expression as a ratios of QL and QH, we will be able to get a numeric value because we know what are the values of TL and TH. So what when you want to replace any of these values, we have three heat flows, okay, QL, QH, and Win. When you want to replace any of these, what you can do is you can draw a hypothetical boundary layer around your heat pump. And you can see that there are three streams, and you can write an energy balance. In this case, you can write W dot in plus Q dot L equals Q dot H. Okay. So that is your energy balance. Now you can use this to replace your W in. So when you replace your W in, you can write it as QH minus QL divided by QL. And you can further simplify this as Q dot H over Q dot L minus 1. Now, we know what is this QH over QL, right? Instead of QH over QL, I can write it as TH over TL minus 1. Now we know what, so I got this part, okay, from here, from this relationship. Now we can easily get the value of this one because we know TH is equal to 535 Kelvin and TL is equal to 460. So my answer is going to be 0.163. All right, any questions on that problem? Now, let me emphasize on few of the things here. One thing that you guys must do when you have one of these questions is draw this diagram, okay? So you should know how to draw this diagram. Then you should be able to write this energy balance equation. In a case of reversible system, you can write this, relationship between heat flows and temperatures of the reservoirs. But remember, these temperatures has to be in Kelvin. Okay? You cannot use centigrade or Fahrenheit values. They have to be Kelvin or Rankine, absolute temperature units. And then you can, if you are finding the efficiency, or if you are finding something like this, the value that you are trying to find, okay, you can get rid of W figure using a high energy balance equation, and then you can get a ratio of temperatures to get the answer. So do you guys have any questions on this problem? Okay. Now let's look at a similar problem, okay, but this is a refrigeration system. Now in this question, I'll explain a little bit and give you a little more time to complete the question. In this question, we have a claim from the producer that the COP of this equipment is 1.3. Now we can calculate our maximum COP COP of the coefficient, or this is actually the efficiency of the refrigerator. We can calculate its maximum value. Okay. This happens, the maximum value of the coefficient of performance is given to us when we have irreversible conditions. Okay. Or in other words, when we have the condition QH over QL is equal to TH over TL. Okay. Now, we can calculate this coefficient of performance, and if the coefficient of performance is larger than 1.3, that tells us that the manufacturer's claim is feasible. If COP maximum is lower than 1.3, that tells us that the manufacturer is lying. Okay. So the question is how to calculate COP max, right? Now, let's try to draw our diagram. Now, always we have two temperature reservoirs and our device refrigerator. Now, refrigerators and heat pumps, in our previous question, we discussed the heat pump. They operate in a very similar manner. Like it's exactly the same thing. Okay, mechanically, it's the same thing. Thermodynamically, it's the same thing. Okay. The only difference is, in a refrigerator, our focus or our goal is to remove heat from low temperature reservoir. Okay, this is our desired output. So when it comes to calculating efficiency, we talked about desired outputs and required inputs, right? So when it comes to refrigerators and heat pumps, both W in is the required input. But when it comes to a refrigerator, our desired output is QL. If it was a heat pump, desired output is going to be QH. Okay, in this case, we have a refrigerator. So this is our desired output. So we can write an equation for COP. COP of this refrigerator is going to be equal to QL divided by WN. Okay. QL divided by WN is going to be our coefficient of performance. Now, we are trying to get rid of W terms in this case again. Let's write an energy balance for this system. Okay. So energy balance is going to be W dot in plus Q dot L is equal to Q dot H. So we are going to get rid of this W in. We have Q dot L divided by Q dot H minus Q dot L, right? So now it's just a matter of getting these values into this equation. Now you can memorize these relationships, but it's easier to do the maths and get it. Let's turn it around. Okay. So you have QH minus QL. You don't have to show all of these steps when it comes to doing these problems. If you can do the calculation properly, okay, simplification properly. Now we have this, and we can convert this into Q dot H over QL minus 1. And we can turn this again to COPR is equal to we can write this as TH over TL minus 1, and we can turn this again to say TL over TH minus TL. So you can see if I substitute QL with TL and QH with TH, I could have gotten this equation. Okay, so that gives us the value to be 5. I did the calculation earlier. So that is going to be our maximum coefficient of performance. So in this case, the manufacturer is claiming the coefficient of performance of his refrigerator is 1.3, which is quite lower compared to maximum COP. So that is a feasible coefficient of performance. So any questions on that one? All right, seems like you guys don't have any questions. So make sure that you watch all the, that you go through the worksheet. Worksheet for chapter 6 is extremely important in my opinion, okay? So make sure that you complete the worksheet for chapter 6 and let us know if you have any questions for chapter 7 through the discussion portal.
For mad years, like how many times were you broke?
Do you have a question, Oscar? All right, that's fine. Yeah. All right, if you guys don't have any questions, that is all we are going to do today.
Thank you.
Sure, no problem.
Thank you.
Sure.